Hello and welcome to Toddcast 52. This is going to be continuation from Toddcast 51. We talked about free radical halogenation um, in that Toddcast. This one is going to be the selectivity. So we alluded to the selectivity being very high for bromination, minimal for chlorination, and we're going to look at what the fallout means if you're doing synthetic chemistry. And whereas, again, halogenation reactions in a practical world that we live in nowadays are far less than they were years and years ago when this stuff was studied. But what we learned from halogenation reactions can apply to so many other areas that we want to thoroughly study it here so that I can look at it down the road. So, for instance, the fast reaction versus the reaction that goes slowly but forms perhaps a more stable compound. That's something you'll learn known as kinetic control versus thermodynamic control. This is a very similar concept. So we're not actually doing like comparing which one goes faster to which one forms more stable, but we're definitely comparing the faster it goes, the more side products you get, which is similar, not exactly the same, but similar concept. So we're going to get into that. So want to look at a little more complex molecule than what we've been looking at. So we looked at methane, alluded to ethane at the end of last podcast. This one, I want to look at propane. And the reason I want to do this is because this now has terminal carbons and an internal carbon. So the reactivity may not be exactly the same. So we learned that free radicals earlier, that methyl is less stable than primary is less stable than secondary is less stable than tertiary, which are less stable than resonance stabilized. And so because of this, um, you may, during this reaction, just may have more of one than another. The more stable one is going to have a tendency to exist to a greater extent. So want to look at just two factors here. Theoretical distribution based on how many of each type of hydrogen you have, and actual distribution. So the theoretical distribution of this reaction, X and X are the same, so one X is going on, that makes no difference. But all the H's are not the same. By symmetry, these three H's on this methyl and these three H's on this methyl, if I draw a line here, reflect one another, so they are similar. They are primary. So altogether, we have 6 primaries. And then these two, the ones on the central carbon, are secondary. We have 2 of those. I just want to emphasize that we have 2 secondaries. Actually, I should color coordinate. 2 secondaries, 6 primaries. So the theoretical distribution, if there was no preference whatsoever, if primary free radicals and secondary free radicals were all equally stable, if this molecule rotated in such a way that the free radical could get to any of the H's equally, then you should get 2 out of 8 being secondary and 6 out of 8 being primary, meaning any of these 6 H's could be replaced by the X. So in theory, the X could end up here, which I've shown it, but could also end up here or here or here or here or here. It could end up in any of these 6 spots, and it would still be one halo propane or one chloropropane, one bromopropane, whatever halogen I'm using. Okay, so I should get 6 out of 8. So there's 8 total hydrogens, 6 out of 8 are primary. So I should get 6 out of 8 doing that, and 2 out of 8 doing that. That's what our theoretical percentages are. So in theory, these 2 can go on to form this, these 6 can go on to form this. I'm going to use this one just to represent all 6 of these, and you should get a distribution with no preference. A theoretical distribution, 2 out of 8 is 25%, 6 out of 8 is 75%. So that's where that number is coming from. 8 possible sites, 2 out of 8, 25%, 6 out of 8, 75%. Okay, so if we actually got that, it would show there's no preference. But what we find is it doesn't quite work out that way. It isn't 25 to 75. It's actually more along the other way around. It's usually around 75, 25 for that previous reaction. So And I should be careful. I had that as a generic halogen reaction at an unknown temperature. So let's look at the same thing a little more specifically. Here's the propane molecule. And again, 3H is here, 3H is here. So our theory was 25%, 75%, but our actual was 56 to 44, meaning the secondary was considerably more reactive. So we have to come up with some mathematical way to get a relative reactivity. And it simply comes down to comparing the actual ratio to the theoretical ratio. So if you were inclined to do math in your head, it's basically this. Some number times a theoretical ratio is going to equal the actual ratio. That multiplier is the number we're fishing for. Whatever I multiply 1/3 by to make it equal to 56 over 44, that is how much more reactive secondary is than primary. Okay, so that's if you're mathematically inclined. Assuming you're not, then let's set it up in a mathematical way. So the ratio of secondary to primary, the actual ratio is 2/6. The product, I'm sorry, that's a theoretical. My sincere apologies. The theoretical, the distribution would be 2/6. The actual, oh boy, spelling is a challenge, sorry. Actual ends up being 56 over 44. So it is the same number we did before. And so to figure out what that multiplier is, that's what we're solving for. So if we do that, we find that if we cross multiply this number times whatever that secondary to primary relative reactivity is what we're saying is that is our relative multiplier. How much more reactive is secondary and primary? Where this number came from is cross multiplying 6 times 56 over 2 times 44. So if I cross multiply, I'm going to get whatever that number is. So that ratio, that reactivity number times this equals this. Let's multiply each side. So that multiplier, that number, times 2/6 equals 56 over 44. So what we're going to do is simply multiply 6 times 2, 6 times 2. And that's the cross multiplying we're doing over here. 56 times 6, 50 times 6 is 300, 6 times 6 is 36. So that's 336. 2 times 44 is 88. So the multiplier, which I have shown as S over P, the relative reactivity of S over P, equals 336 over 88. And if you're inclined to just estimate your math, if this was 90 and this was 360, that'd be 4. There's a little less than 90. It's not significant, but a notable amount less than 360. So it's going to be a little less than 4. So if you said 3.9, 3.8, that's a good guess. Probably want to calculate it and figure out what it is. So the multiplier, the ratio of selectivity of secondary over primary is 3.82. Okay, the math here takes a second to get used to. If you have good instinctive algebra skills, you'll blow through this pretty easily. If you don't, take the time to draw it out. The relative reactivity of secondary over primary can represent as number, that relative reactivity number, times 2/6 equals 56 over 44. So the ratio of what you theoretically get for secondary over primary multiplied by this actual reaction factor equals the actual secondary over primary that you get. Okay, so I'm going to erase this. And if we do it for bromination, exact same setup. So this time, my secondary over primary, that's what I'm looking for. That reactivity multiplier, whatever that number is, times 2 secondaries over 6. That's my theory. So this is my multiplier. This is my theory equals actual, meaning what you should get multiplied by the relative ratio equals what you actually get. So in this case, 96 and 4%, that's kind of going to be kind of crazy numbers. This times 6, this times 2, this times 6, this times 2. That cancels out to 1. So the multiplier factor is going to be 6 times 96, which is going to come in just less than 600. So about what? Oh, boy. 576, I'm going to guess, over 8. So 576 over 8. I'm going to say this is roughly 600 over 8. 600 over 8 is around 75. So this is less than 75. So 72-ish wouldn't be that unreasonable number to pick. Meaning, when I do chlorination, secondary is about 4 times as favorable as primary. The secondary over primary for bromination, because it goes so much slower, it has more time to select. So it doesn't resonate over, but every time they bump into each other, if a primary bumps into another molecule, it may abstract a hydrogen and become more stable, and it's probably going to extract it from the secondary rather than the primary. And over time, you start building up more and more secondary. So if the reaction goes slow enough, then you get more and more secondary formed, and you get this preference of reactivity of about 72 to 1. Okay, hopefully the math seems reasonable, but this is how we exploit certain reactions. So if, for instance, you wanted to synthesize a tertiary compound, then you would want to use bromination because it's so selective for secondary over primary. It's going to be more selective for tertiary over secondary. If you wanted a primary alkyl halide for whatever you need, then you're probably going to choose chlorination because it is less selective. The other factor is temperature. The more you heat it up, the faster reaction goes. The faster it goes, the less selective. So if I don't want tertiary and secondary selective over primary, if I want as much unselected primary as possible, I do a high temp chlorination. If I want to have high selectivity for the tertiary or secondary bromination, then I would do low temperature bromination to get more of the higher percentage. Hopefully this concept makes sense. Okay, so now let's consider this was secondary to primary. This is going to be a tertiary compared to a primary. There's 3, 4, 5, 6, 7, 8, 9. 9 H's that are primary to 1 that is tertiary. So my tertiary this time, tertiary ratio to primary is some number, the relative reactivity. So relative reactivity times the theoretical distribution. What you have is 1 tertiary to 9 primary equals, so this time we get 35 over 65. So again, I need to multiply times 9 and times 1, times 9 and times 1. That cancels. So the relative reactivity factor is going to be 35 times 9, which is 350 minus 35, or 315, over 65. So 315 over 65. 65 times 3 is 325. So this is just a hair under 5. So like 4.9-ish is what you're going to end up with. 4.85 apparently. Okay, so chlorination, let me erase my math. It ends up tertiary chlorination is more selective than secondary. So I'm going to reach a conclusion that whatever temperature this was at for chlorination, the tertiary to secondary to primary relative reactivity is 4.85 to 3.82 to 1 for primary. So it will choose 5 tertiary, or it has a 5 times preference for tertiary over primary, a 4 times preference for tertiary over primary. These numbers are not to be memorized because I did not list a temperature. If we vary the temperature, these numbers may go up or go down ever so slightly, not going to be significant. So if you estimate it around 541, if you heat it up, then those numbers might be 4.5 and 3.7 and 1. If you cool it, it might be a little over 5, a little over 4 into 1. So it's there, but they're still going to be in that ballpark. But don't memorize exact numbers. Know the trend. So if tertiary is more stable than secondary, it should make sense. It's a slightly higher selectivity number. Bromination is going to exploit it even more. So the same math again. This time we have the tertiary to primary ratio and the multiplier times 1 over 9, the actual, or the theoretical. And then the actual is 99.4 or 0.6. Multiply by 9, multiply by 1, multiply by 9, multiply by 1. It's going to be about 900, just below 900 over 0.06, which if you do the math is probably coming in 1400-ish, 1500-ish. So a little under 900 over 0.6. So 1491. Much, much, much more preferred for bromination tertiary than chlorination. So for this reaction, for bromination, the tertiary to secondary to primary ratio ended up being 1491 to 72 to 1. It is highly selective. Bromination is slow enough that it takes longer, but you get way more of the tertiary. So again, if you want tertiary, do bromination. If you want primary, do chlorination. And then adjust the temperature accordingly. Okay, lots and lots of math. So now we're going to look at it from the other direction. So the reality is you have to like be able to predict what you'll get. So two ways to do this. Here are my product distributions. So 39.5. So if we were told that the ratio is 5 to 3.8 to 1, then I would have to now take the relative number of each of these types. So if I had an A, a B, C, and D for relative, uh, just your relative carbons by symmetry, hydrogens by symmetry. Let's make sure I can understand which is which. So A product apparently is here. That went on the A carbon. This one on my B carbon. This one on my C carbon. This one on my D carbon. Okay, so I have that distribution. To figure out what these percentages are takes even more math. So there altogether is 3 A's. So if I want to get my A to B to C to D ratio, I'm going to take 3 times 1. That's a relative reactivity for a primary. 2 for B, I only have 1 B, and it's a ratio of 5. To C, I have 4 C's total, and that's 3.8. And then for D, I have 4 times 3.8. Okay, so to figure out the exact percentages, I now need to add up all of those numbers. So the actual percentages, 3 plus 5 plus 15.2. So 8, 15.2, 23.2, plus another 15.2, so 0.4. So 8, and again, sorry, I've lost track, but 15, 15, 0.2, so 30, 38.4. So the percentages will be crazy math, but let's see how this works out. 4 over 38.4. So I predict A to come in a little more than 10%, or I'm sorry, a little closer to 7%. Ends up the math of A a little less than 10%. So 3 over 40 is around 7.5%. This should be a little more than 7.5%. So that comes in about right. 5 over 40 would be around 12.5, a little bit more than 12.5, 13-ish, looks about right. 15.2 over 38.4 is just a hair under 40, just a hair under 40. So these numbers right here become those numbers if you have to predict. Ooh-wee! That's a lot of math. So I'm going to clear everything. You can freeze from it, screenshot it, whatever you need to do. You can always go back and get this. But what we did before was we gave you the ratio and we said the multiplier, some number, times the theoretical, which was the theoretical amount of, let's say, secondary over total, will equal the actual over total. And so we have a couple of things. We solved for this number last time by cross multiplying to figure out what it is by multiplying this over that. This time we went in the opposite direction. Given this number and this number, the theoretical in this, can you figure out what the actual is? Lots of work to get the total, and it's not as easy as it may seem. Okay. The one thing I want like my students to be able to do is make a prediction based on relative reactivity. So in this case, the tertiary really was minimal. But in bromination, because the ratio is so much more substantial, again, it was in that 1600 to 72 to 1. Well, it's like 1491 to 72 to 1. 1600 to 62 to 1. Numbers are already changing. Again, inconsistency because of temperature, error bar, whatever it might be, but still so much larger. You get a substantially larger amount of tertiary. So if you wanted to selectively get the halogen here, you do bromination. If you want to maximize the amount here, you do chlorination, but even then you get a nominal amount and you get a little bit. It still would be a very small amount. Really hard to get that one. These would be the ones where chlorination would be favorable to get secondary because you don't drown it out with tertiary. Lots of math. You will have to understand this at different levels. Like the math here, specific for this topic, but that relative reactivity factor times the distribution, the theoretical distribution, will give you the actual distribution. So the relative reactivity numbers, understand how those work. And they're basically the multiplier that you multiply the ratio of what you have as available reactive sites to the actual distribution of the way the product is formed. Okay, lots of math. Again, probably overwhelming. Make sure you go through it, go slowly, follow through in the math. Math is just repetition. Best way to learn math is just do problem after problem after problem. Even the same problem, it still is going to be helpful. Okay, math is done. Relative reactivity stuff is done. Hopefully this went okay. I don't know. I know traditionally, having taught this for many, many years, it just doesn't go as well as it could. And I push this as my philosophy, and mostly because I went to college at a time where we were not allowed to use calculators, so everything had to be done in our head, including really complicated calculations like that. The more you do that, the better feel you get for numbers, though. It becomes really helpful. So I would suggest trying some of these without punching the calculator and then just use the calculator to double check. But that said, we are done with this podcast, and I will see you at the next one.